way off in the distance, we can just see the brand newly installed solar panels. When we landed here this afternoon, all we saw was the wire frame that we highlighted in an earlier video, and now we have the solar panels all ready to go for the interferometry experiment that is going to hopefully be trying to get a handle on some of the early hydrogen formed in the universe from the very first generation of stars. Okay. So this is Joelle, and you might remember her from such greatest hits as setting up the antenna and setting up the solar panels. And now Joelle's going to be explaining to us what's going on. Why did they go to all this work? Why the slogging around for days in the mud and fiddling with computers on the backs of giant solar panel arrays? What is it we're trying to find here, Joelle?
Yeah, so what we're trying to do with this particular experiment is that we are trying to make a picture of the sky at radio wavelengths. And that can be a little confusing because you can think, you know, what does that mean to make a picture at radio wavelengths? And it basically just means that, you know, light is an electromagnetic spectrum, and you've all seen pictures of the sky at the visible wavelengths, which is what we can see with our eyes, but there's a whole lot going on out there that is beyond what we can see at different frequencies. And this is just one example. It's not at the frequency ranges that we're looking at, but I just kind of want to show you what it looks like to see the sky at a different frequency / wavelength than what you're used to.
So what is this wavelength here?
408 megahertz.
408 megahertz. And what does that translate to? So if my kids are familiar with like radio waves and microwaves and stuff, where does that fit in that type of terminology?
So that's radio. That's a radio wave. And for a bit of context, so FM radio, the radio that you listen to in your car, that's high 80 megahertz to 110 something megahertz. Yeah. So this is just a bit over 4 times the FM radio that you listen to in your car. Yeah. And yeah, even though this looks kind of, just like a splotch of color, it actually really is a picture of the emissions of the galaxy at radio wavelengths. And we have an Oreo for demonstration that I get to eat later. Yeah, okay. So maybe you've learned that the Milky Way is a spiral galaxy. So, it'll be roundish, obviously not completely round. That would just be a spherical galaxy. But it'll be kind of flat like a disc. And there are these spirals. There's the center where it says Oreo. And then there will be like spirals coming out, and we actually live on one of the spirals on the very outside of the spiral. So it's as if you were sitting on top of this Oreo and you're trying to look out into the universe around you. You're sitting on the edge of the Oreo, and you're kind of looking in towards the center of the Oreo, and this really bright stripe would be kind of the body of the Oreo or the galaxy, right? And that's why it's so bright, because that's where all the stars are. And even at radio wavelengths. So if you saw this picture in visible wavelengths, it would look similar in terms that it would be a really bright stripe at the center, because that's just, we're on the outskirts looking in. And yeah, so on the outside over here, it's all darker, or less bright, because it's outside the galaxy.
And what do we call this little bit sticking up in the middle here?
That's if I'm not mistaken, and I can't Google anything, but if I'm remembering correctly, that's called the Northern Galactic Spur. Okay. So it's in the north sky, and it's a spur.
So when Joelle says she can't Google anything, let's put this in perspective. It's not because she's not tech savvy. She's an absolute beast at programming. But like, we're literally living in a shack right now, way up in the high Arctic. Yeah. And so there's no internet up here. But anyway, so that's the visible spectrum, the Oreo. That's your radio frequencies at 408 gigahertz. What are you doing up here? Like, you built this telescope, you designed your little rack for holding your solar panels. What's going on here?
Where do we go from here? I think this is a good one. Yeah, so basically that really beautiful picture that I showed you, which is this one, which is just lovely, lovely, lovely. This is at 408 megahertz. And, when you go further down in frequency, so you start getting longer wavelengths, so you go to, let's say 10 megahertz, which, if you're a fan of amateur radio, for example, people use amateur radio communications at these low frequencies, like tens of megahertz. We have tried to make maps, similar looking maps of the sky at lower wavelengths, but they haven't turned out super well for a variety of reasons. And so this is just an example of a bunch of the existing maps at lower frequency. So for example, this one is at 38 megahertz. And we were looking at 400-ish before, right?
Okay, so,
and it looks like a very far cry from what we saw before.
Yeah. So these are studies you're saying that are just, they're kind of incomplete, right? Like they've got some data for some parts of the sky. We're missing parts of the sky. Maybe there was a pole in the way and the telescope couldn't see past the pole, maybe, right? But when we look at that, so on the other graphic Joelle has here, which is a great way to kind of corroborate, and we talk a lot about, you know, showing your sources. So that's really what Joelle's doing here. So she's got these 8 different views of the sky at slightly different radio frequencies, and then she's created this lovely little graph for us, so we can see the 38 megahertz one she was just talking about. There we are. Yeah. And that corresponds to this blue line, which I'm guessing is
Turtle.
Yeah. So that's a 1962 study. Yeah. So a lot's changed since 1962. Yeah. In terms of telescope and computing powers and stuff. So yeah. What is it that you guys are doing? What is it you're looking for then? Yeah. And so
broadly, that is what we're trying to do. We're trying to create a map of the sky to improve upon these maps at these lowest frequencies that anyone's ever looked at. You know, partly just out of scientific curiosity. You know, we want to have an understanding of the whole electromagnetic spectrum from our own galaxy. But there's a bigger motivation behind this experiment in general, and it's the kind of pursuit of this elusive signal from the very early universe, which is the 21 centimeter signal, because it comes from a transition of neutral hydrogen that emits light at 21 centimeters wavelength. And that's what this plot is kind of showing here. It's a theoretical prediction of what the signal would look like. You know, it kind of just looks like a squiggle, but there's actually a lot of really interesting science that you can learn from, like the depth of this dip, for example. And this is, you know, plotting the frequency as a function of frequency, the temperature of this theoretical signal. And I say theoretical because it's been predicted, and we know that it should exist, this signal, because there's hydrogen everywhere, especially in the very early universe when it was mostly hydrogen, right? Because we're looking for this signal from before the first stars and galaxies formed, so it was mostly hydrogen. And there's this prediction that we should be finding this signal that kind of just looks like a squiggle right now, but
so a lot of theoretical physicists have sat around and said, oh yeah, based on what we know about hydrogen, the way that electrons join up with hydrogen, the way that they emit photons, we should get this signal. Yeah. Okay, which is not at all unlike the theories that came out about the echo of the Big Bang.
Or general relativity even.
Yeah, and we know that as those things have played out years later, people have found evidence of them, such as the W-map. So, Joelle's got some actual images here.
Yeah, so that was just, the squiggle that I was showing you before was kind of like an average of the signal over the whole sky. So, you know, there's a lot of different ways of thinking about signals that come from the universe. You can either make a picture, kind of like the ones that I showed you, but you could also just take an average of the emission over the entire sky. So that one was an average, and this is an actual picture of what people think the signal would look like, right at the end here.
So this is what we have today?
Yeah, so this is all this stuff here, all of these ones. This is just stuff that we don't care about. Well, we kind of care about if you're an astrophysicist or cosmologists. So we care about the cosmological signal, which is kind of hidden behind all of this messy astrophysics. So this is galactic emissions. This is all galactic emissions, all of these here. And these are extragalactic, so from other galaxies. And then this is the cosmological signal, or a theoretical prediction of what it would look like. And many hours of simulations have gone into producing a picture like that.
And you guys are going out to try and find some evidence.
Yeah, exactly.
That says that it actually looks like that. Yeah. So let's see. Now, as I said in an earlier video, these guys achieved first light yesterday, right? Yeah. So they have one of their 2 telescopes up and working. And they were able to get some data yesterday. Yeah. And
it looks terrible.
Joelle's not happy. Like, I'm not going to lie. She's been moping around here all day. I could blame it on the weather, but we know that she's not happy with her data. So, what's wrong with your data, Joelle?
Well, so
Theoretically, what should your data have looked like based
I'll show
on
you some previous
experiments?
Yeah, so this blue line is actually theory. Because you can, as you can simulate signals that come from the universe, you can also simulate what the signals that your instrument will read look like based on some assumptions, right? Okay. And so this blue line is actually just, you take the galactic spectrum that we think we should be seeing, and then you work in some of the response of your instrument that you're supposed to know, and you get this blue line. This red line is from a couple of years ago, when they did a kind of really basic run of this experiment.
Similar equipment to what you set up?
So same antenna, but very different everything else.
Okay.
So it was just the antenna and like a battery and the little board to record data. So we've scaled it up significantly since this was done. But yeah, same antenna. So it should, in principle, look a lot like this. So again, this is frequency. This is just, like the spectrum from the galaxy, and this stuff down here is just radio frequency interference, or RFI as we like to call it, and that's just inevitable. That's from the ionosphere, but the rest is just wiggles from our instrument.
This here is sunlight, solar particles streaming in, bouncing around our ionosphere, and giving off a tiny little bit of radio wavelength photon.
And actually mostly communications, human radio communications that are being bounced around by the ionosphere. Okay. So that's called shortwave radiation.
Right. So we talk about light pollution in class, where light from the city goes up and bounces around visible particles in the atmosphere. You're saying that radio waves. So all you kids on your cell phone right now, you're screwing up her experiment. All right.
And Elon Musk with his satellites.
Okay.
That's another one.
Let's back this up. Let's take a look at this data here.
Yeah.
So you said that you're not happy with it.
No.
Show me what's wrong with it. Because I see this beautiful little blue line here. It looks awesome.
Well,
what's wrong?
That little blue line, so what we're seeing here, so we take data from our whole night, and we ran for like 12 hours, let's say. No, it's not bad, yeah. It's a good night. And then we want to see what the minimum temperature that we read overnight. This is basically an analog for temperature on this axis, the sky temperature, right? So minimum, blue line is minimum. Red line is the maximum that we measured over the whole night, and then we have mean and median too. Okay. So we just want to see like the statistics of what our antenna was seeing overnight, right? And so the blue line looks okay, but actually not even, because this thing is haunting my dreams right now.
This 60 megahertz?
Yeah, right around 60 megahertz. There's this weird thing, this weird feature that like is persistent throughout the whole night. Another cool thing you can do is you make a plot like this, which is basically each slice represents one of these like blue or red lines that we were seeing before, and so it's kind of like a time stream of what your telescope was seeing over the whole night. So if you took one slice,
4:48 a.m.
Yeah, but this is UTC, so -4, so at midnight.
Okay, so we started this at midnight and ran till middle of the afternoon.
Yeah,
right?
but it's just a chunk. There's more data. Right. But anyway, so if you zoom out a little bit, you can see this weird feature at 60 megahertz that I was telling you about. That matches up with this bright stripe.
Okay.
And
so the color here is an intensity?
Yes, exactly. Yeah, so it's literally like if I were to take one stripe, one slice of this plot, it would be something that looks like that.
At one instant of time.
Yeah, exactly. So time is on this axis. Yeah. And that thing just should not be there. That's not in our previous data. So I have data from other experiments. Oh, these all suck. I was just testing it out. Okay. But basically, we've done this before in other locations, and we've never seen this weird thing at 60 megahertz. So we have no idea what it is.
All right. So
yeah. And then all this junk here is also other stuff that we don't know what it is. So there's just a lot of junk.
Yeah. But this is day one.
Yes.
And if we haven't already covered this, if you're watching this video, we covered it in earlier videos as Larry was explaining the nature of why they're coming all the way up to the Arctic to do this. Because, as we mentioned, ionosphere, right? Yeah. So even though they started this at midnight, okay, even though they started it at 12:48, midnight. I just want to point out that right now it is 10:20.
Oh my God, really?
And when we look out the window, that's what we're looking at. So yes, we got some fog right now, but yeah, that's not a normal 10:20 for those of us who live anywhere below 70 degrees latitude, right? Like, I guess normally we have some darkness time, but we don't here in the Arctic. So you came all the way up here in the Arctic in order to get the best information, because it should be away from this little noise from human pollution, but also because what's going to happen?
The sun's going to go down for 6 months. Yeah.
And hopefully
that's
a lot of that
exactly
will go away.
Yeah, exactly. And camp is going to close down. So what we hope is that a lot of the stuff that we're seeing here is noise from just the camp in general, you know, like people with their laptops and inverters and stuff.
Laptops, inverters.
Yeah.
Steven on the walkie-talkie.
Yeah,
looking
exactly.
For
Hi.
half the time.
Yeah.
The noisy campers that were up on the ridge with their big radio antenna and kitchen tent. So
you had a radio antenna.
Hopefully when some of that stuff goes away. So I guess what we're looking at here is the fact that data is going to change as conditions around this data change.
Yeah.
Right? So again, yes, obviously we want to try and explain this away. You want to be able to try and figure out why this is happening. Maybe you do figure it out. Maybe you don't figure it out until next year when you set up 2 more telescopes 10 kilometers away and you get to start comparing, and suddenly you end up with some overlap. But in the meantime, this is what we call an anomaly. Okay? It doesn't fit the pattern. We don't know why it doesn't fit the pattern, but it's important right now because it probably means something. Maybe it means that Tristan forgot to tighten one of the nuts on the antenna. Maybe it means there's a piece of zip tie in the way. Who knows? But it probably means that the more data you get, you can start to figure out, oh, well, now if we run a second thing at whatever time of day, we run it from the second antenna, that goes away. So now we know the problems in that first antenna. So this is what we call the troubleshooting, kids.
Yeah.
You're going to have to go back, do more tests, recook that data.
Yeah.
But don't ignore that. Like, that means something. That means something. And again, like if we look at the next data set here, a lot of that goes not away, but it changes, right?
Yeah.
So the moral of the story here is when you set up an antenna in a week instead of the 2 weeks you'd originally figured you were going to be up here because you were just sitting in Resolute eating peanut butter cookies, sometimes things might not be perfect. So a couple more days of data crunching. You're up here until when?
August 10th.
August
maybe.
10th. It is now Saturday, July 23rd. That gives you 18 days.
Oh my God.
Okay, so you got 18 days. Marco is going to be keeping Joelle company. He's really thrilled about that. But they got 18 days to
figure this out.
Number one, get the second antenna up and running. Maybe some of that goes away on a test from the second antenna. And maybe just different days, different data.
Yeah.
There's low-flying birds. There's airplanes going by. Who knows? Data mysteries.
Yeah.
But don't ignore your anomalies, kids, because anomalies is how we found out about blue dwarfs and red giants and all the other stars that are out there that don't fit the HR diagram, which we may or may not have talked about before this video. But the anomalies are important. Don't lose them.
Yeah.
Thanks very much, Joelle.
Thank you.